just going to pass these back. I don't know what the averages are. He just got them to me. I'll tell you that later. I understand there was an electromagnetics test on Friday. Is that right? So that might have explained for some of the lower grades than average. I mean, there were plenty of high grades, but there were also some rather excessively low grades.
So, things really better. Everyone's coming here right after digital on test Friday.
I'll just go put it.
The thing too, I want to make sure everybody knows this. If you have any suggestions, I'm trying to do my darndest to get this information across to you. The best way I can think of doing is presenting some theory and working problems that you have concerns about. I've always felt providing a solution is a good thing to students. This is my personal feeling. And if you're a good student, you're going to struggle with it without looking, and then see if you get the right answer. If you don't, find out your mistake. That's generally the way I did it when I was in school. And I spent probably, however old, I mean, I wasn't one of these people that was a stellar genius. We had the guys that were the perfect SAT, perfect ACTs in my class. I remember one, I had two of them right next to me. And all these courses were graded on a curve. That made me real happy. But here's the thing about it was, I was determined, so I would do, in physics, they would give us the answers to every other problem. I would do literally every other problem in the back of the Tipler book and compare my answers. I did that stuff with engineering and everything. It took a lot of time, but that way you learned it stayed with you. It was permanent. And I did it, anything that was assigned right after class if I could. It helps. But if you got suggestions, I'm open to it. If you want me to do something more with, I guess, some kind of slides, I'll do that. I hate slides myself, but just let me know. Now, today what I'm going to do is, first, are there any questions? I'll put the solutions to these quizzes up. The quizzes were just things where you did the Laplace transform of the source, found the transfer function of the system, took the source times the transfer function to get the output, and then did partial fractions to get the time domain form. There was nothing tricky at all about this. This was just the standard things we've been doing forever. But there were some very low grades, which made me concerned that you didn't understand circuits and you didn't understand Laplace. So please make sure you catch up on it. Any other questions before I get going? I'm going to do one final thing before we do the Laplace transform. All right, now, here's the thing with Laplace transforms that make it so powerful. We can realize real transfer functions. As engineers, this is important. This is synthesis. So suppose I have a function, and I'm making one up here. Suppose this is the function I want to synthesize. I have h of s is equal to, say, 4s squared plus 5s plus 1 over s squared plus 4s plus, say, 6. Now that's arbitrary. It's a function, for some reason, I want to synthesize an electronic components that will make that will do this transfer function. Follow me, everyone? So now we're going to do it. Now I know a couple of things. First thing I know is that for me to do this, I have to do it in terms of a negative feedback approach. Do you all remember that? Where I broke it up into two functions, and I had one as 1 over 1 plus the AB. Y'all remember that, class? And I had the first function by itself. So the first function will be the 4 plus s, but before I do anything, I have to divide top and bottom by s squared. You remember? I have to divide everything by s squared. The coefficient of the s, or the highest order of s down here, has to be 1. First time I did this, it was s cubed. I'm only doing s to the 4th here because it would be s squared here. Otherwise, it would be just too much information. So when I do this, I get 4, right, plus 5 over s plus 1 over s squared. And downstairs, I get simply, this is going to be this function times 1 over, and this function is going to be 1 plus 4 over s plus 6 over s squared. Okay? Now this is my first function I'm worrying about, and I'm going to call it h1 of s. This is my second function, and this is h2 of s. And when you multiply the two, you get h of s. So when we take these, just multiply them, we get our function. Now, for the...
What did you do? Did you divide everything by s squared on the top and bottom?
You remember when we did this? Everybody, how many remember this? Sure. This is standard synthesis. We had to do it this way, right? So now, when we get to this point, I'm going to take this h1 of s and show you how to do it. So this is h1 of s. Here's where my input feed is, my x of s. Right? First thing I'm going to do is take 4. So I want to block with 4 in it, and I want to do it with electronics. My simple answer to that is this. I'm going to have R and then 4R here. All right. Now I know what comes out of here is going to be minus 4 times x of s. Do you all agree with that, class? Give me a show of hands if you do. I know there's a minus there, but where it's going to feed into is a summer, and the place it goes next is going to be R. I'm going to put them all in here. Now, what this summer will do is take the inputs. This is going to be the input 4 times x of s, right? Only it's minus 4 times x of s. And then this r and this r are the same, so you're going to get minus that coming out. Follow me? But this is a summer circuit. How many remember the summer? All right, that's the first part. This just takes care of this 4. Next, I need a 5 over s. So now I take some of this signal, right? And now I need the 1 over s. Correct, class? How do I achieve the 1 over s? I do this. I simply get a circuit where I have a resistor, capacitor, right? Negative terminal, positive terminal here. Ground that. Comes out here. That's C. This is R. I make a note that RC product is 1, right? And now I know the impedance of this is 1 over SC. Correct, class? How many see this right here? What's the output at this point? It's going to be 1 over RCS, or 1 over S with a minus sign, minus 1 over S times X of S right here. How many see that? You all see it? Right there? Remember, this is a simple inverter. From here to here, if you look at this, the impedance there is 1 over SC divided by R, right? It's Z2 over Z1 with a minus sign, or it's minus 1 over S times the input X of S is this, right? Now I tie this right here, right? And now the output from here, whatever that is, if this is V2, the output here is going to be whatever that is, V1, right? Plus V2 plus V3, only it's minus those, right, class? And the reason I like this is because the minus here and the minus here cancel each other. I don't need to put the inverters on. Understand? I don't have to put the sections of inverters. So I tie that here. So now I've realized this part right here. Finally, what do I need? I need to take some of this, right? That's already got the 1 over S form, doesn't it, class? And I need another 1 over S, correct? How many see this? Be honest with me. Now, this is straightforward. We've gone through this. I haven't had you build anything like this, so we build it with the building block approach, just blocks. But now I'm doing it with electronics. Now this signal right here is 1 over S X of S, right? Now I feed it through another stage where I take another R, another C, right? And this is 1 over CS. That's negative, that's positive, ground that. And now right here, I have what? X of S, right? Times minus 1 over S, correct? Right? And then I have times another minus 1 over S here, don't I? So it's minus 1 over S times minus 1 over S. It's really 1 over S squared X of S, correct, class? How many see this? So for this one, I need an inverter if I'm going to tie it to that. So now I just put a simple inverter here. Ground that, and and make that R. Make that R. And then feed that right there, and voila. Now this is from input to output right here. I can call this Y1 of S. This is H1 of S. How many C? Yes, sir.
Isn't your 1 over S term off by a factor of 5 then? If RC is 1, shouldn't it be 1/5?
This one, I take it, you're absolutely right. What I should do is put this as 1/5, right? Right? I really should have this. It should be R times C, really, is going to be really,
1/5.
yeah, 1/5. I'm sorry about that. You are absolutely right.
Then
All right.
inverter would have a.
And then what I have to do is take this as 5. I'm going to have the inverse, because this is the factor of 1 there. So then, if this is going to be 1/5, yeah, because it's 1 over RC, give me 5. Then here, what I need to do is take the factor RC here and say it's equal to 5. So it'll cancel that. And that, thank you. Yes, sir.
Why did you say you didn't need an inverter?
I don't need inverters for this one because this is going to be minus 4XS right here, right?
Okay.
And then this input to output here would have a minus 1, right? Since you got a minus times a minus, you get rid of them. That's the reason I did this. How many understand why I don't have inverters? I let that's negative effect, so they cancel, right? But here I'm going to need one, right? Because I've got this stage and this stage. And for this bottom part here, the RC product has to be 5. And then now I have H1 of S. Give me a show of hands. How many see that? Now, you're going to tie this right here to the next stage. That would be H2. And I'm going to draw, if you don't mind, I'm going to erase this first part right here, just to give myself a little room. But I bet you see what's going on, because this is getting interesting. So we got, what, 1, 2, 3, 4, 5 op amps, and a bunch of R's and C's. But nothing extravagant, right? We don't have anything very hard to do. This is a trivial thing to implement. Now, for the bottom part, remember, for feedback, the way I'm going to show you the block diagram. In general, you have a forward gain, A. Oh, sorry, the summer's not there. And then back here, if this is X of S, and this is Y of S, then your feedback here is a beta factor. This is the flow of the signal. And it feeds back negative, and that's positive. And this is the summer, right? Follow me in this class? How many remember that? And you know the overall gain for this, H of S, this is H2 of S, right? That's equal to A over 1 plus AB. Agree, class? Now, you'll notice that where B is and where A is. The trick for R's, when we look at this, the A here is 1. Everybody see that? We just have a straightforward gain of 1. So what we do is get rid of A and just put 1 in there and put a 1 in there. All right? Now, when we have that, the next thing we do, and it's pretty straightforward if you think about it, we've got that first one implemented. Right? Everybody agree with that? That's the electronic implementation of the block diagram that I did before of a simple synthesis approach. Now I'm going to do this part. All right. Now I want to match this with this. What do you see? I know A is 1, but B is what? Or beta.
4 over S.
That's right. 4 over S plus 6 over S squared, right? Agree, class? Now take a look at this. So here, I would take this output, I'm feeding it. So I'm just going to, what I want to do is block this over so I can show you. So now here comes my output, Y1 of S. And now that's feeding into something. And the feed has to have a feedback approach. This is positive, This is going to be negative. I'm going to draw this first. And it has this type of approach from the output right here, where this is y2 of s. Some of this comes back. I have to first enable a 1 over s stage here. And then I take that and I'm going to feed it through 4 here. And that's going to come over here. And that's got a negative summing effect, so it's going to go this way. And then I need another 1 over s here. And then it's going to come over and feed a 6 here. And then that's going to come up and be part of the negative summer effect as well. Do you all agree with that, class? I want to show the blocks on this one first. That's 1 over s. Now I'm going to go ahead and implement that one. But I drew it so you can see it. Negative feedback's a little tougher to see than the first part. Follow me, class, on this one? And the far back guys, can you see it? It doesn't matter. Probably not even in here. All right. Follow me on this? So I'm gonna erase that part, okay? All right. All right. That's the summer, correct, class? I've got a positive value of y of s going in there, so the first thing I need to do is take, if I'm going to use the negative approach, I've got to do the inversion for y1 of s. So if this is where y1 of s is, I'm going to put it through a simple circuit like this, where that's r, negative, positive, ground that, and then I start my summer. This is going to be the second stage summer. This is this right here. Follow me, class? Everybody? Yes, sir.
Why is it 4 and 6 subtracted from the sum?
Remember the format? This is 1 over 1 plus 4, or 1 plus AB, right? 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 So what did that come from? From this diagram, didn't it? Right? All right. See how that's negative? That's the reason. You can actually prove this to yourself. If you take a look, what's the signal here? It's x of s, right? Minus beta times y of s, right? And then it's times 1 equals y of s. You group the y of s's, you're going to get this equation right here. You go ahead and check it, all right? That's the reason, because this is negative feedback. Now, when I take a look at this, I'm doing this summer right here. I had to invert the y1 of s because I know that this summer is going to have a negative additional effect. We're going to add up all the values here and negate them. So I wanted to make sure that y of s was negative. Follow me? Now, which is really x of s, which is y1 of s. Next thing that comes into this, I need a 1 over s stage, right? So now I have to have a 1 over s from y of s, and this is the output right here. That is my y2 of s. So now I need to take make sure I got this. That's y of s. Yeah, it's feeding into the summer. Right, now I need to take some of this right here, and I have to have a 1 over s, so I can take this, bring it back right here, and just get an r. Over CS here, and ground that. This accomplishes this, the 1 over s. Now I need to multiply that by 4. So right here, it's really going to be the factor 1 over s. Now I need to multiply by 4, And I can do it this way. Actually, yeah, I'm going to do it this way intentionally. I'm going to go ahead and put this is going to be equal to R. This 4R right here. This comes out, that's negative, that's positive, ground that. That's unfortunately what's effectively done is negative, negative is a positive. So now I need to negate this, and I'm going to go ahead and put a stage on where I just have a follower, or inverter I should say. And these do get a little messy. So this section here takes care of this right here. Agreed with me, class? Now, the next part, I'm going to have a negative, negative is a positive, and then times 6, so I need another 1 over S. So I take some of this. This is where it gets messy. And I'm going to go this way, and I'm going to put a resistor. This is 1 over CS. Comes out, ground that. This is just going to have RC be 1 in all these. The product of RC and all these is going to be 1. You follow me, class? You're going to have to do this, trust me, on the final exam, so you better know how to do it. You got to really be attentive here, because this is one of those things that kind of tells everybody if you're an engineer, if you can focus your way through the stages of this, not lose focus, do it correctly, you're probably going to be a good engineer. If you get bored, start fumbling things, don't know what you're doing, that's when trouble occurs. Just remember this. You'll be required to do this. This is basic too, by the way. It's not high level. Now, go ahead. I couldn't hear you, but
He said, yay, triangles.
Lots of triangles.
triangles. Well, for the record, you're going to find out when you have WYSIWYG things on the on your design card. You can just pull those things, and it's easy to do. You've used PSpice, haven't you, or LT Spice, things like that? You can draw these things up in seconds. Yeah. It's not fun when you got to freelance and freehand them. So now I come down here, I have the 1 over S right there, and now I need 6. So now I put in another stage here where I'm going to have an op amp. That's going to have an R, and then this R is going to be 6R here. Comes out here. And I know what I've got going here. That's 1 over S. That's negative. This is going to be negative, so it's positive. This is going to be negative. Now I got what I want, and I can come right up here and feed it in, and I'm going to go this route and just plug this as R. And there, I've done the whole thing, where if I take those two circuits and stick them together, now I've implemented the actual transfer function. Do you follow me on this? I know it's messy, the first time especially, because I'm doing this on a board, and I haven't laid this out carefully, where I have all the triangle, all the op amps laid down vertically. I've just done it the way I wanted you to see it all. And I do the block diagram on the second part, because that's the one that gets people. How many see what I did? All right? I've showed you this. It looks like a lot of trouble. Here's why this is, yes sir.
I was just wondering if you could go through this part, this Y2 of S, and explain sort of the negatives and positives.
Sure.
Just
All right.
as you go through it.
So what we're doing is this, right?
Right.
And the way I'm implementing this is via this, right?
Right.
So I know I need a summer, and I need something that's going to effectively have this. It has a 1 over S times a 4, another 1 over S here times a 6, and both of those are feeding in negative to the summer, correct?
Right.
So when I take a look at this, this is my summer, right? So when I take a look at that, I know the first thing that goes into the summer is going to be Y1 of S, but I invert it, so it's negative here, so when it comes out it's negative, but it's just added, right? Follow me? And that's, that's this, X of S would be Y1 of S.
Right.
All right. Next, I'm going to go ahead and I need the 1 over S and a 4. So I take some of the output right here, right?
And that output is negative right now or positive?
No, that's the final value is positive, right? This is what we want. This is the y of S. It comes out. Now this implements the first 1 over S. Now I'm going to take that and I have to multiply that by 4, right? This implements the 4. Then I have to take that, invert it, right? Because I want it negative, and then I feed that back. That's that point.
Wait, are you sure you need the last inverter? Because if you want it to be subtracting and then it gets inverted again.
All right, well, let's just think about it. That's y of S. This is minus y of S over S, right? Correct?
Oh, okay.
And then what? This is going to be it's going to be plus 1 y of S over or times 4 over S, right? So I need to get this to make it minus again. Correct?
But doesn't the last inverter, wouldn't that make it plus y of S again? Like-
No, this times this is minus, right? I mean it's
I
plus.
mean, the summer, because the summer inverts the sign again, doesn't it?
This has to be minus here because this will do it again, another minus. All right? Right?
Yeah, I'm just, because,
Tell you what, do me a favor, work through this. If I'm wrong, show it to me. I think I'm right on this one.
you're right.
All right, don't worry. Just trust me on this. It gets a little tedious. All right, that's that part. Who asked that? You did. And the next part is going to be this part right here. Now I need another 1 over S, right? So here's my first 1 over S. I break it through here. I got another 1 over S, but it's positive. I don't want positive. So I stick it through here. This gets me the negative. That should be grounded, by the way. That gets me 6 times 1 over S squared, right?
Right.
It's got the negative sense. Bring it back up there, and I just feed it right like that. All right, that's it.
So each one of those op amps essentially inverts the signal?
Absolutely, because I've done it all, tying the positive 1 to ground. Yes. Oh, I thought you were going to hit me. You got a question?
This summer, it does not need an inverter at the end.
No, because it's taking the negative and inverting it. Just work the math on this one. You'll find it does work. Yes. I know if you would like nice clear blocks. Summers means summers. They add and add. If you wanted a pure summer, you can do it the way you're thinking. I can put the negative part of the sum there, then put an inverter, and then I can put all positive voltages in. All right? I can do that. I just didn't want that many stages. Yes.
So just to confirm, going into the summer, it's negative y1 of S, and then positive.
Think about this. The summer I have here does what? It takes it's going to say it's minus the sum of V1 plus V2 plus V3, right? Isn't that what the output is? It's minus V1 plus V2 plus V3, correct? So if I want actually positive out, I'll make V1 have a negative sense to it. So it's my whole thing is I'm dropping 2 stages is basically just work this out and know how to do this. This is good stuff. In the book, he shows examples of this. And I want to tell you one other thing. You're going to see the real benefit of this in 1 second. I know it's irritating. You're wondering, who cares? Well, you'll care because this is something that makes you a lot of money in the future. I found that most students, when it comes to how do you win at gambling or make money, they're a lot more serious. You know, abstract thought, who cares? But money's different.
Dr. Finchie.
Hold on, let me just get this.
I was going to ask a question. I was saying you could do the same effect using like an appropriate RC combination.
What's that?
You could have done like the same, like getting that 4 and the 6 using an RC.
Yeah. There's so many
I was making
permutations.
sure.
I just kept it simple. Now, if you have your books, if you look on page 158 and 159, this is chapter 4, he goes through, and there's a discussion of exactly what we talked about. If you have your books, 158, 159. He goes through the basic implementation of very simple circuits using summers and using op amps, just like we did. But he takes his good old time building the real deal. And on page 162, he starts with a very simple one. By the time he hits, I try to do this thing in a way where you don't have to go through all the painful stuff that he shows you about transient response and all that. But then he says in 38 through 40, he wants the direct form realization of, and he gives you either impulse response, differential equations, or transfer functions. Now what I'm about to show you is, everything I've done is in S, right? Why did I do it in S? Because it's Laplace transforms of things you're used to and you can do. Here's what happens in the real world when they're doing these. They assume S just becomes J omega. Let me show you what I mean by that. I'm going to show you the power of this. All right. Now, follow. Suppose I ask you to implement a circuit that will do this. I could say if I had second or let's get rid of this. Say second derivative of y with respect to t squared plus 2 dy dt plus y equals 4 times dx dt plus 2x. All right? I want that implemented, where x is the input, y is the output. That's a standard filter response. Why did I give you that? That's the form the boss gave you. Your boss gave you something that a mathematician gave him that he wants implemented, so he can put any input and look at any output. All right? Voltage. Maybe it has to do with a rocket control system. So he wants a system that you build that will do this. And in his case, he wants an analog, not a digital. So first thing you do is turn this into something that's got a transfer function form. So we're going to take a Laplace transform on both sides. All these problems assume no initial conditions. Laplace transform approach means this is going to have a y of s. Second derivative brings out s squared. First derivative, s. 0th derivative, just a constant 1. Agreed, class? Other side, what happens? Anyone? Take the x of s out in front, and I have
4s plus 2.
Thank you. 4s plus 2 here. Now, transfer function. Think about it. Ratio of output to input, right? Now my h of s, the transfer function for this system, will be y of s over x of s, correct? Remember, you're going to build it. What next? What is that?
4s plus 2 over the other.
That's right. All right, there's the transfer function that describes the differential equation your boss gave you. Now he wants a circuit that builds that, because he wants to put any voltage in and look for any voltage out all the time. You could do this with MATLAB. I just want to tell you, yes, in fact, you could have something where if it was on, you could feed any set of inputs and give you any set of outputs. But your boss wants you to build it. So how do you build it? With the realization 2 I just showed you, you would divide top and bottom by s squared, right? Correct, class? This first part would be that linear thing where you had a summer, you multiply by 1 over s, then by 4, right? Then 1 over s squared and by 2, correct? Put them into the summer. Down here, you get the form of 1 over 1 plus beta, right? And then you would do this in a negative feedback form, and you would build it with operational amplifiers and hand it to the boss. For any given input, you give any given output in real time. Follow me? That's what would happen. That's a realization. How else could he have done it? He could have gave you information where he had an h of t, correct, class? Suppose he says h of t is equal to t times e to the minus 5t u of t plus e to the minus 6t u of t. Just suppose this is the function he gave you. And he says, I want you to build a system that does that. What do I do, class? Laplace transform that first. That's the first step. What do you get? That's going to be 1 over what? S plus 5 squared, correct, class? Next one, what? 1 over S plus 6. Here you could build it several ways. Let me just explain. This is a very simple pole, isn't it, class?
Yes.
Can't we build that with one simple op-amp where I have what? I have a resistor R1, and then the output I have a capacitor in R2 in parallel with it, right? How many remember that? Sure. Now that'll give it an inversion of it. So then you would have to put it into a summer anyway, because you're going to add this to this, correct, class? How many feel that if they are asked to do that, they could build a circuit that would implement that? Give me a show of hands. If you don't, you should. You need to learn how, because you're going to be asked to do that very thing in Stride. All right? So if you're going to do that, just for the record, so I can make sure you can see this part's straightforward. This is going to be something where you're going to have R1, right? Then you're going to have an operational amplifier, ground that. Then you have a capacitor, and I'll call it C1. Then another resistor, R2. Now that is still going to be inverting, right? This is going to be your X of S come there, or X of T, either one. And it's got to go into a summer. That's going to implement this part, right? Do y'all agree? Show of hands here. You can calculate the values at R and C. And it's going to have a negative to it, but you know how to deal with that, right? What about this part? How about that part twice? How many see that? Take it once, put it in series with a second, right there. How many see that? Right there. Then when you put the input there, and the input to that one, now you've got to feed them into a summer. What's a summer? Just a couple of resistors in parallel that feed the negative terminal, right? And the output comes out, you make sure the R's are the same, and low, you can implement that. How many see this? You may not believe yourselves, but you can do this one. It's easy. And it should be something where, if you're getting this stuff should be very obvious. Yes, sir?
So how do you take the output of the first one that has a different RC and implement it into a second that wouldn't be affected by that?
Oh, you mean, how can this impedance not affect that impedance? Is that what you're getting at?
So when you put it through a second one, how is that not affected by the impedance that you have?
Remember, these stages, all right? If I feed this into, say, this. And this output, right? And you're saying, well, what about this impedance? Doesn't it affect this net impedance here? Is that what you're asking?
No, I was saying, so you're saying take the output of that and put it through another one to get the 1 over S again?
If you wanted to implement this, you would do this. You would have some R1, R2, C, call it C2, right here. Negative, positive, right? Feed that into another R1, another R2, another C2, right here. That's it. 2 stages.
Okay, I thought you were saying.
That's what I'm saying. Don't worry about your thoughts. Go ahead.
I understand that's 1 over S. How would you get 1 over S plus 6?
No, this is not 1 over S. This is going to be what? Come on, guys. What's if I looked at Z2 here, what is it? Z2 is equal to what? 1 over R2 plus C1S, right? Right?
Uh-huh.
Divide by C1. Then I get what? 1 over C1, that goes away. C1. That's S over plus a constant. 1 over R2C1 is going to be 6. Go through the, follow me on this stuff, work at it. It's real important. Got it, class? This is what it's all about. Now I always get hung up on this stuff, but it's very important you see this. Now here's why it's so important. Just listen. In the real world, I showed you how you could take this function, the boss could give you this, he could give you this, maybe he gives you a set of, I don't know, y of t versus x of t, and you have to pull off that information. You have to find an h of t. Follow me? You have to find the impulse response or something like that, and you have to finally get in a form you get a 1 over s. Then you build the circuit. Now, another thing that can happen, I want to tell you this. Is this. If I'm looking at a frequency response of a system, normally it's h of omega, or instead of s, h of omega. Let me explain this. And they'll have something. We're going to talk about just magnitude there. Now, if you have an h of s, the only thing you do is say h of s then becomes simply j omega, and you work the equation that way. Follow me? And now, if you look at this, omega is 2 pi times the regular frequency in hertz. So your h of s here is a ratio of input to output versus frequency, right? Not s, not complex frequency, but against real frequency omega. So if you have an h of s like this, say h of s is equal to 2s plus 3 over 5s squared plus 6s plus 1. H of omega is equal to 2 times j omega plus 3 over 2 times j omega squared, or minus omega squared, plus 6 times j omega plus 1. Do you follow me on this, class? Now you have real and imaginary components, correct? But you have to get the absolute value of these things. Well, absolute value at the top would be what? It would be the square root of 3 squared plus what? It would be quantity 2 omega squared, right? Square root of that. Wouldn't it, class? Follow me on this? That's a real and an imaginary number. Down here, the real number would be 1 minus 2 omega squared. The imaginary is 6w, or 6 omega, right? Now, you'd have to get the magnitude of that. How many understand that? All right, magnitude. Once you get the magnitude, if you plotted it versus frequency, if this is versus omega and you plotted the magnitude of h of omega, you would get something that may look like this. It's going to asymptotically go to 0, guaranteed, because there's a 1 over s squared in the bottom. And then you could see it. You could see the plot. What you're going to be learning to do in the future is you want this frequency plot. Say you want this. You want this h of omega. So how do you get it? Well, first thing you do, if this is just a picture, you do what's called a least squares error fit of several coefficients in the polynomials, and you develop something. Now, first thing I do will get my h of omega, all right? And I'll show you how to do that later. The next thing you do, once you have h omega, you get an h of s that represents it, and that's easy to do because we just reverse engineer that, and then we go ahead and build that circuit. Follow me, class? Now, this is what I was getting at with Dr. Bose, or Professor Bose. What Bose did was this. His speakers had an output power versus frequency that stunk, like that, something like that. The higher the frequency, the less power they got out for every watt they put in. So What he did was had a filter that did this. It did the exact opposite. So the product of the input of, you say the filter response times his speaker response was constant, flat. All right, and that's how he made all his money. He just used his head. He got rid of the effects of the inertia of the cone. The higher the frequency, less power you get out per hertz, and less power watt per hertz, the higher the frequency. So he got rid of that problem, and you'll see the power of this when you actually do designs. Hopefully you will, your own design. Now, that sort of concludes Laplace transforms right here for now. Next thing we're going to do is be talking about Fourier transforms. Has anybody here had Fourier transforms? You have. What class did you have with?
That was an internship. I got bored.
You got bored and they just appeared? A vision? Thank you. Well, if you've had them, congratulations. You're way ahead of the game. Now, let me explain to you about Fourier transform. I know some of the stuff I've shown you here seems to stretch you. You will do well, believe me. Everybody here is meant to be an engineer is going to love this and get it right. But your first time through it is always just like convolution, not the thing you signed up for. Nevertheless, you have to get through it and you'll learn. Now, when we talk about Fourier transforms, let me explain this. Fourier transforms are different than Laplace transforms for two reasons. The definition of a Fourier transform, x of omega, is equal to the integral from minus infinity to infinity of x of t times e to the minus j omega t dt. Contrast that to the Laplace, x of s of the same signal, is equal to the integral from 0 to infinity of x of t times e to the minus st dt. All right, now, look at the difference. Here, the Laplace started 0. Here, the Fourier started minus infinity, which means something to us. This is more of a purely mathematical exercise, but it's not quite that true. Here's the reason. When you record data, oftentimes if you're an engineer, you start at 0. All right? It just makes sense. That's not always the case. You can get a data record that goes from minus 100 years to plus 100 years that you can't change, that you have to work with. All right? So just understand, data availability has to do with a lot of this. But more than that, this is the fundamental definition. This takes care of every possible time x of t exists. All right? Existed. From minus infinity to plus infinity. You'll notice one other thing, though. That's just minus j omega. Now, since s is equal to a real value, sigma plus j omega, you could say that x of really omega, or the Laplace transform, is equal to x of s, right here, becoming j omega, if and only if x of t is non-zero for t greater than 0. Let me explain this. If you take this and you just let s be simply j omega, I get that, don't I? And if x of t is 0 for any time less than 0, then fundamentally, if you got the Laplace transform for a function, you have the Fourier transform by just taking and replacing s with j omega. Do you follow me on this, class? Let me give you the easiest example to see. You know that if I have x of t equal to e to the minus at u of t, the Laplace transform of that is what? 1 over s plus a, right? Does that function is that 0 for all time less than 0? Yes, right? Sure, just one look. How many see that? Come on. Yes, of course it is, right? All right, so that means what I just told you is I can take this Laplace transform, and if I want the Fourier transform, the only thing I can do is take S and make it j omega. So this says that it would be simply, this would be the actual Fourier transform of this signal. Follow me on this, class? So for an entire class of signals, almost all of them that we've done, matter of fact, all of them we've done, you can get the Fourier transform by just taking the S in the Laplace transform and taking the S there and replacing it by j omega. Understand? It's that easy. Now here's some you can't do that for. And I'll show you. Let me just finish this thought and then you can go. Because this is really important. Fourier transforms are very obvious and you're going to see some real power in this later. I'll get to it. This is extremely important for electrical engineers. Laplace and Fourier, I can't tell you how important they are, man. Now, suppose I have this functional form. This is going to be the time domain. The height is 1. That's tau over 2 minus tau over 2. This is ye olde pulse function, right? Well, that has values that are non-zero for t less than 0, doesn't it? Here, the Fourier transform, you need to calculate. Matter of fact, I'm about a minute over right now. We'll do this one, but you're going to see that this Fourier transform and several that are symmetric about t equals 0 become critical in our understanding of Fourier. I'll take you through that next time when we meet on Wednesday, and I'll give you some more comfort with the synthesis stuff.